Well, let's continue to look at model fit statistics. Here, there are a couple numbers we want to check into. First, multiple R square, so which is equal to 0.1857. That means with our model, with all the covariance predictors we introduced into this regression equation, we're able to explain 18.57% of the variation in the dependent variable. In this case, is income in $1,000. And then we also have adjusted R squares. That is R square, you know, taking into account the model complexity, that is number of parameters. That number turns out to be 0.1827, slightly smaller than the R square here. So adjusted R square is smaller than R square by taking into account the model parameters. Parameters. The interpretation is almost identical. Then we have also F statistic, which is equal to 63.08 with 2 degrees freedom. Denominator degree of freedoms is equal to 1383, and numerator degree of freedom is 5. Basically, it is a test. This is the F test of overall model fit by comparing this model, okay, with all these parameters and a model with intercept only model, okay, and we get this F statistic, which is equal to 63.08 with 2 kinds of degree of freedoms, and the p-value is almost equal to 0. So here we should feel free, comfortable to reject the non-hypotheses that the two models are similar. Okay, that is the full model here, the current model, and the intercept only model. Okay, the non-hypothesis is that all slopes, excluding intercept, they're simultaneously equal to 0, and that can be rejected. That means at least one of the slope is statistically significant. Well, in addition to providing interpretation of parameter estimates, including intercept and slopes, we can also provide other kinds of post-estimation analysis. For example, prediction. So, for example, here we want to know what individual who is 35 years old, why female, so female, white. Then for black and other, these two dummy variables, they're going to be set to 0. Then that denotes a white person. And with sample average education, we want to know that individual's predicted income in $1,000. So we're going to create this data frame here, this hypothetical x vector. Okay, then we're going to feed it into this predictor function, right, using my OLS. That is the OLS estimation result object, and we're feeding the new data here we just created, and we want to know the confidence interval too. We run this, we get the results. So based upon our model and prediction for this individual, that is 35-year-old white female with sample average education, would expect her predicted income to be 30,000, okay, $125. And then we have a lower bound and upper bound, a 95% confidence interval for our prediction. And that is, we are 95% confident that the population, the predicted individual, okay, in the population would have an income lower bound at $27,458 and upper bound to be 32,079, 32,000 and $791. Well, sometimes people are interested in taking difference into predictions. So here we can actually create another data vector, by changing some of the value here, then feeding to the predict function again and get a result. And we can simply take a difference of these two results and get a difference in predicted uh, response value, predict response value. Okay.